Okay, now let's look at chapter 10. So we'll do the chapter 10 today, and chapter 10 we're going to spend, okay, according to the lecturer notes, okay, we're going to spend 2.5 hours in this chapter, but most probably I will finish it in 2 hours. All right, so it's, this week and a week after holiday. Oh yeah, before this, let me remind you guys, don't forget that there are three ongoing program right now. Okay, so for Paul Leader Physics, make sure you join Telegram's group. So I've already posted the name list in your group a few days ago. All right, and also there are two more programs. One is known as a Physics to You, and one more is known as Physics Buddy. So all of you, you have to attend a meetings tonight, if I'm not mistaken. All right, remember to refers to the notice in your group again. Okay, so for physics buddies and physics to you, you have a meeting, and then for a Paul Leader Physics, you have to join a Telegrams group. Okay, and then for Paul Leader for all subject, okay, Paul Leader for physics, science com, chemistry, science com, yeah, chemistry, and then chemistry and biology and mathematics. Okay, you all will be in another program known as VIP programs. So that one, you guys will discuss amongst Paul after a Paul physics meeting. All right. So right now, the things that you have to know is Paul Leader for Physics. You have to join Telegram's group, and then the other two groups of students, which is the one involved in the Physics to You, and one involved in the Physics Buddy. You guys have to attend a meeting according to the notice given. So remember, all right. Okay. Now let's look at chapter 10. Chapter 10 is about wave. This chapter is very, very similar to previous chapter. Why? Because both of them, they involve a sine graph, okay, sinusoidal graph in their motions. So you have to know how to do a graph sketching in this chapter. So first, let's look at what is wave. Okay, so simple harmonic motion is a motion. It's an oscillation. The object is moving in a periodic motion. Wave, even though it has the same graph, but it's a totally different things. Okay, it is a propagations of a disturbance that carries the energy and momentum away from the source of disturbance. So the important things is you have to know it transfer energy. All right, wave involves a transferations of energy from one point to the other point. But the important thing is, okay, now let's go to bullet point number 2. So mechanical wave is defined as a disturbance that travels through particles of mediums to transfer the energy. Now, this is what I told you just now. Okay, and then the particle oscillate around their equilibrium position. Okay, they oscillate, but they do not travel. Now, what does it mean? So let's say now you have, okay, a series of particles. All right, all these particles. So this is the particles along a string. All right, this is the particles along a string. So initially, all these particles, they are not moving. So what happened? Okay, what happened by this hand? The hand on the left hand side is that now it start to move the first particles. All right. So it start to move the first particles. So this is a person's. Okay, the person is holding it. All right, and that's okay. He or she start to oscillate this a string. So what happens along here is that now the energy is being transferred to the first particles, and this first particle is start to move. Okay, and then the particles will then transfer the energy to the next one, and energy is being again transferred to the next one, transferred to the next one. So what is moving is actually the energy. The particle itself is not moving. What happens to this particle is that it just moves up and down, oscillate along its, okay, it's a vertical direction. So it's oscillating. Okay, it's oscillating. So the oscillation, the vertical displacement changing as the energy passes through it. So this is what we see actually. All right. So every particle is oscillating along the motion. And then only energy is being transferred. So when you join their line together, okay, when you join their vertical displacement together, okay, that is one of the reasons why we see a wave. So it's oscillating in the vertical motion. And then if you join the line together, you are seeing a wave here. All right. So remember, particle is not moving. The one that is moving is the energy, and then what happened is that the particles is oscillating in a vertical direction. Okay, so in this chapter, basically you're going to see two types of displacement. One is a vertical displacement, okay, vertical displacement. Another one is a horizontal displacement. So you will have displacement in a symbol X and also the displacement in symbol Y. Both of them, they refers to different things. All right, so this is what happens in wave. Particle is not moving. The thing that is moving is the energy. All right, so it's involve a transfer of energy from one point to the other point. So what happened? One person's or one situations happen, okay, and it generate the first energy. It causes the first energy. Okay, it give. It's not generate. It transfer the energy to the first particles, and then the particles start to oscillate. Okay, and then we can see a waveforms being generated. So now we have either, okay, we have a water wave, sound wave, wave on the strings, wave in the springs, and then the seismic wave, okay, the earthquake wave. So there are a few types of wave, and what we are going to see in our syllabus is the progressive wave, the wave that I show you just now, all right? So actually there's another form of a wave, okay? So there's another type of motions, or maybe I can explain it to you as well before we proceed to progressive wave. So we have another wave which we call longitudinal wave, which happens in sound wave. So initially, we also have a lot of wave, a lot of particles. All right. So okay, and then what happened? Okay, let's say this is okay. Maybe you're talking. Okay, you're talking. So when you talk, it generates wave, right? So what happened in this wave is actually now is oscillating along X component. So every particle is oscillate. Okay, every particle is oscillate to the left and to the right, to the left and to the right. But again, the particle is not moving. It's just oscillating at its original position. So what happened is again the energy is being transferred. Okay, the energy is being transferred, and when it reaches the other person, he or she can hear, okay, what you are talking. So this one is a speak, okay, and then this one is a listening. All right, so you can, he or she can hear what you are saying. Why? That is because of the transfer of energy. So what happened is that when you're talking, the energy is being transferred to the particles, to the air particles, and then they are oscillating. Remember, just oscillating. Particles, they are not moving, but they oscillate. And when they oscillate, they transfer their energy to another particles, and the another particle is transferred to the following particle, to the following particles until it reaches the other person. All right. So these are the wave that we have. Okay, this is the wave that you learn in your secondary school, longitudinal wave, and this one is called what already? A progressive wave. All right. So okay, now next, or mechanical wave. Okay, so this we call mechanical wave because we are looking at the particles. Okay, so it involves a source of disturbance. So that's why I say when you're talking, when something happens, a special occurrence happens, so it transfer the energy to the first particle. So it needed a source. Okay, you need a source to initiate the wave. Okay, and then a medium. So you need a medium. That is what I keep mentioning, the particles. Okay, so particles transfer energy. So source of disturbance and then a medium, okay, that can be disturbed, and then a mechanisms to transfer the disturbance from one point to next point along the medium. Okay, so the mechanism is the one I showed just now, how it oscillates. Okay, so one is oscillating in the vertical motion, another one is oscillating along the horizontal motion, horizontal component. So progressive wave. Progressive wave is defined as a wave propagate continuously from a source of disturbance. Okay, the progressive wave have a definite speed called the speed of propagations or wave speed. So wave speed is what happens in this red color line. All right, so okay, our discussion is going to focus more on the first case. Okay, we're going to focus more on this one. So propagations of wave, when we talk about wave motion, when we talk about anything about wave, we are actually talking about this red color line. Okay, this is what we call wave. All right. And when we talk about particles, we are talking about this blue color thingy. Okay, blue color particle. So this is particle. So in this chapter, our calculations, it involves two things: the oscillations of particles, which we are going to use the concept that we learned in chapter 9, simple harmonic motions, to solve it. And another one is what we call wave motion, the red color line. So it involves two types of motion in this chapter. All right. So progressive wave, you're looking at, okay, the wave propagate from source of disturbance, and then it has a definite speed called the speed of propagation. So you are looking at the speed of the red color line just now, okay, or the wave speed. So the directions of the speed is in the same directions of the wave propagation. All right. So it starts from a source and then it propagates in a directions in the distance. Oh yeah, this is a transverse wave. Yeah, the names I forgot just now. So transverse wave is a wave which the directions of vibration is perpendicular to the directions of wave. So you see the directions of the vibrations of particles. So particle is moving in the vertical direction, okay? Because like I told you just now, this spring, okay, this wave actually is made up by a lot of particles. Okay, it's formed by a lot of particles. So what happened is that the particle is oscillating, is vibrating in a vertical direction, right? So yeah, it's stuck again. Okay, so it's vibrating in a vertical direction. So it's oscillating up and down. Okay, so it's oscillating up and down, up and down, up and down, and so on. Right? So it keeps oscillating. So what happened here, okay, is the particles, the motions of particle is in the vertical direction, and then the wave is going in the x component. Okay, so this is the directions of wave. Directions of wave. The one in the red color. Okay, the wave is propagating. So this wave is moving in this direction, right? And then you have a vertical direction, the directions of particle. Okay, this is the directions of particle, right? So directions of particles, directions of vibrations of particle is perpendicular to the directions of wave propagation. So the wave is going to the left-hand side, the particle is moving up and down, as shown in the diagram here, right? So the directions of the propagations and the directions of particle vibrations. So the examples is a water wave, the wave on the strings, and etc. So water wave is the easiest things, okay, easiest examples that we can observe in our daily life. Try to drop drips of water into a pose, okay, into a into a lot of water, right? So maybe you prepare some water here. All right, so this is maybe just a bowl here, a bowl of water, and then you drop a drips of water on top of it. All right, so satu titik, you drop it. So you will see, you will observe the wave light, okay, the wave, you will observe it. So this is a water wave, okay, and examples of a transverse progressive wave. And then the second types of wave is what we call longitudinal wave, okay, the wave in which the directions of vibrations of particles, okay, is parallel to the directions of wave propagation. So this one, the wave also propagate, okay, as you can observe in the diagram, the wave is again, okay, moving to the right-hand side. But what happens to the particle in it? Okay, like what I told you just now, the particles in this spring, okay, is oscillating back and forth, okay, to the front, to the back, to the front, to the back. So it's just keep oscillating. The particle itself is not moving, right? So what you observe here is actually the compressions and expansion. So you can see in the spring. So when you oscillate the spring, when you move a spring, the spring, it won't move, right? What happens is just it's oscillating. So actually it just represents what happens in the particles. It's oscillating, okay? Particles in the spring is oscillating back and forth. So the example that we have, the typical examples that we have, and we're going to discuss in this chapter is sound wave. All right, so our main focus in this chapter is actually the sound wave in a subtopic number 3. All right, so for the first one, the first example in the transverse progressive wave, the one that we use in our calculation, we're going to refer to what the wave shape, and then the things that we're going to discuss here is a sound wave starting from 10.3. Okay, so 10.2, we discuss the shape of transverse wave. 10.3, we discuss what happens in sound wave. So the calculation, basically, we're going to focus on the transverse wave. So the properties of wave. Okay, so figure shows a periodic sinusoidal waveform. So what we have, okay, we have a new terms here, in which we call crest or peak. Okay, so from crest to crest or from peak to peak, that represent one complete oscillation. Okay, and then from trough to trough, the other one here, okay, it should have another one here. That is also called one complete oscillation. Okay, so this one, it represents the minimum of the wave, minimum, and then the crest or peak, it represents maximum. So sometimes questions will mention from maximum to maximum, from minimums to minimum. Okay, right. So maximum to maximum means from crest to crest or from peak to peak, and then a trough to trough is from minimums to minimums. So along these motions, we have a vibrating particles, and then from the center lines to the maximum line, we call it amplitude. Okay, so we have two types of amplitude. So either a positive amplitude or a negative amplitude. All right. And then from crest to crest, from peak to peak, you see we have a lambda here. So instead of time, this chapter we have another one called lambda. Okay, the wave motion, it involves the wave speed. So one lambda is the distance traveled by a wave, okay, for one complete oscillation. Distance for one complete oscillations we call one lambda. So period is the time taken to complete one oscillation. All right, lambda is the distance traveled through by the wave for one oscillation. Okay, distance traveled in one oscillation. So remember, lambda and period, these two variable, we only use it for one complete oscillation. Okay, one complete oscillation. All right, so we have two types of wave in this chapter, two types of graph in this chapter. Okay, so this is just a head up for you. We'll discuss it in the following subtopic. So the first one, we have Y against T graph, which is for particles. Okay, which is for particles. And then another one, we have a Y against X graph, which talk about what happens in the wave. Okay, Y component represents the particles, and then X component represents the wave propagation. Okay, so we have the same shape of a graph, just that two of them, they represent different things. Okay, they represent different things. So there are some important quantities that we use to describe the wave. Okay, so now we are going to look at all these terms. First one, displacement. Okay, we have a Y displacement. So displacement Y is the distance moved by a particle from its equilibrium positions at every point along the wave. So in which it means, okay, this is the equilibrium position. So when the particle oscillate, okay, when the particle oscillate, every particles, they have different Y. All right, that's why just now we have a graph of Y against T. Because the positions of the particle, it changes with time. Okay, so when it's oscillating, as you can see here, the first one, okay, it is lying on the equilibrium position. The second one, it moves a bit. The third one is slightly more than the second particles. And then the third one, it reduce again, it decrease again. Okay, and then it goes back to the original position. So the vertical components, the Y displacement, it changes with time. Okay, it changes with time. So every particles along the wave, they have different Y. Okay, they have different Y, except the one lying on the equilibrium position. So this is for the Y displacement. Okay, displacement Y. So when we talk about displacement, we are referring to the particles because the particle is oscillating along its equilibrium position. It keep repeating the same path. Okay, it just the only difference is the directions of oscillation is going up, down, but along the same path. So we use displacement to describe the distance traveled by the particles. And then we use the term distance to describe the wave propagation, the wave motion. Okay, so Anda kena berhati-hati. You have to be careful with the term that is being used in this chapter. Okay, next one, we have the terms called amplitude. Okay, it is the maximum displacement from equilibrium positions to the crest or to the trough traveled by the wave motion. All right, so it is the maximum distance. So what is the things that we need to put in the table? So that is our, okay, A is equals to our Y max or Y maximum. The maximum value along the Y component, the vertical component, equals to A. Okay, equals to A. So the maximum displacement traveled by the particles from equilibrium position, that is our amplitude. So frequency is the numbers of complete cycles that pass a given point per second. So again, F is equals to 1 over T. So we have seen it in the previous chapter. And whereas for period is the time taken for particles to complete one oscillation, or the time travel for the wave to travel one wavelength. So instead of one oscillations, now we also relate it to one wavelength, because wavelength is also the things for the information for one complete oscillation. All right, so T is equals to 1 over F. All right, it is something that we have seen in the previous chapter. Okay, now angular frequency. Angular frequency is the rate change of the phase of the waveform. Okay, so again, it is something that we have seen in the previous chapter. Basically, omega is equals to 2 pi over T, or it is equals to 2 pi F. So it has two equations. And then wavelength, the distance between two successive crests or trough, and then the distance between any two successive identical points on the wave. Aha, now what does it mean? Okay, what does it mean? Two successive identical points. So they have two positions, okay? They are lying on the same position. So let's look at the wave. Okay, I'm going to sketch the wave once again. So 1, 2, 3. No, I don't like it. Yeah. So this is the wave. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. Okay, now. So this is the equilibrium position. All right. So what does it mean by two successive identical points? So it means the 2 points that are moving towards same direction and located, okay, same direction, and they are located at the same displacement, okay, same displacement. All right, so let's look at the sketch the diagram that I sketched on the right hand side. So what does it mean? Okay, so if you look at this position, okay, these particles, it's moving upwards. Okay, it's moving upwards and it's located at the second particles, okay, second object. So the one that is moving towards same direction and located at the same height is this particle. Okay, it's this one. So the two particles that I color the blue color, I put in the blue color, these two we call identical point. Why? Because both of them, they are moving towards same direction, which is a positive Y direction, and the distance from equilibrium positions, they are the same. Okay, so they have same value, they are moving towards same direction. So we call them identical point. So for two successive identical point from these positions until this position, okay, we call one lambda, one wavelength. All right. So let's look at another example. So if I'm going to take another point, for example, this point. Okay, this point. So again, this point is going upwards, right? And then the following one, okay, this one is going down already. Okay, it's moving downwards. It's decreasing actually. The direction is going down, even though it still has a positive Y. Okay, the direction is going down, positive Y, but direction is heading down. So this one is also heading downwards, even though it's a positive y. Okay, so I'm going to change the directions a bit. So it has same y value, but now the direction is going down. Okay, this direction is going down, this direction is going down. So these two green color particle, both of them, they have same y, and then they are pointing towards same direction. Both of them, they are now moving downwards. So again, these two, we call them identical point, right? So this is also one lambda. So sometimes in a question, they will ask you to identify which 2 points they are identical. So this is how we distinguish. Okay, this is how we identify. You look at the directions of the motion first, the directions of the particles, and then you check their y value. All right, if they have same y value and if they are heading towards same direction, then we say they are identical. Right, we say they are identical. Okay, now wave numbers, we have one more things here, okay, one new quantity, which we call K, wave number. So what does it mean by wave number? Wave number is the numbers of wave exist in 1 meter. So K is equals to 2 pi over lambda. Okay, K is equals to 2 pi over lambda. So period is a time taken, okay, is a time taken for one oscillation. Frequency is the number of oscillation in 1 second. Wave number is the number of wave in 1 meter. Right? So their definitions, they are very similar. So make sure you know what is the difference. Right? So F, K, T, they are very similar. All right? They are very similar. All of them, they are for a certain, they are happening at a certain condition. F, numbers of oscillations per 1 second. K, numbers of waves per 1 meter. Period. Okay, time taken for one oscillation. Okay, time taken per oscillation. Okay, so we have F, K, T, and also lambda in this chapter. Okay, so this 4 quantity, we are going to use it very often in our calculation. Okay, in our calculations and also in graph sketching. So in this chapter, we need to know how to sketch graph, and now we need to know how to do the calculations. So basically, lambda, F, K, and T, we can split them into 2 family. Okay, K and lambda, we often use them together. F and T and also omega, we often use them together. So these 2 family, you're going to use them very often, and then you have to know how to change what from one to the other one. Okay, so macam mana nak tukar daripada satu ke satu lagi. So basically, this is how. So for the first family, K is equals to 2 pi over lambda. All right, so this is for the first family. For the second family, we have omega equals to 2 pi over T, which is equals to 2 pi F. So this is the second family, the equations that we use for second family. All right, so the questions might give you lambda, might give you K, so you need to know how to find the other one. And also same things here, the questions might give F, T, or omega. You need to know how to change it to the quantity that you need, either in the calculations or in the graph sketching. All right. Okay, so the last term is what we call phase angle. Show the relationship between the vibrations of one particle to another, okay, in which we use a delta phi. Okay, if delta phi is equals to 0, then we say they are in phase. If they are not, then we say they are anti-phase. So basically, you see what happened. Okay, this symbol we use to describe what is the difference between 2 particles. What is the relationship between 2 particles? Okay, so if they are equals to 0, then we say they are in phase. Okay, if they are equals to pi over 2, then we say they are anti-phase. Okay, out of phase. So yeah, this one we'll describe it later on. So I'll skip it for now. So now let's see how to form equation. So a figure shows progressive wave profiles moving to the right. Okay, so the wave is moving. Okay, the wave is moving. So initially we have a solid line. Solid line represents the shape of the wave at times t equals 0. Okay, and then the dotted line, it represents what happens to the shape of the wave after a times equals to t. Okay, so the whole wave is moving. the wave is shifting. Okay, so that's why we say wave has a motion. We call it wave motion because the wave is actually keep moving to the right or to the right, not to the left. So figure shows a progressive wave profile moving to the right. Okay, so in this case, how are we going to form the equations? So the general equations for the wave, okay, the general equations for the wave, the equation is very similar to the one in previous chapter. Okay, but now we add a bit of things here. Y bracket X and T. So what does it mean? Okay, what does it mean? This equation, this bracket, it means Y changes with X or changes with time. Okay, equals to A sine bracket omega T plus minus Kx. So basically Y changes with two items. Okay, it changes with times and also it changes with X. Okay, the distance traveled by the wave. Right, so we have a plus minus sign here. So why is it so important about this plus minus sign? Because it tells you the directions of the wave. Okay, if you have a negative sign, okay, I think it mentions right here. Okay, if it has a negative sign, then it means the wave is going to the right. Okay, so for the here, okay, for the next one, you put it here. So y, okay, y, and then bracket xt equals to a, oops, sine omega t, all right, minus, okay, minus kx. So this one, it means the wave is now traveling to the right-hand side. So if you have y bracket xt equals to a sine omega t plus kx, then it means the wave is now traveling to the left. Okay, so to the right and to the left, they use different symbol and you yourself must memorize it because questions will ask you form equations very often. And you yourself have to know when to use positive and when to use negative. Okay, kamu sendiri kena tahu bila kena letak positif, bila kena letak negatif. Because quite often questions will ask you to form equation. All right. So now let's go back to the original equation. So the general equations, okay, this one we call general equations, the one with a plus minus sign. So y and then with a bracket x and t, it means y changes with x and also changes with time. So based on this equation itself, we can actually sketch two graphs. Okay, we can sketch the graph for y against t. We can sketch the graph for y against x in the following subtopic. So equals to A. Now A is amplitude, sine omega. Omega is our angular velocity. T is the time. Now this small letter t, it doesn't represent capital letter T. It could be any T, okay? And then a plus minus kx. K is the wave number and x is the distance of particle from origin. Now it uses distance of particle from origin. Why? Because just now we say every wave, it got a source. Okay, it has a source. So let's say this is my source. This source transfer energy to the first particle. So they keep oscillating, And we say the positions of the particles, they are not changing. Therefore, the distance is always fixed. Okay, so this is what we call distance. This is what we call distance. Okay, or maybe from here to here. Okay, this is another distance. So the distance of the particle from origin. So this is our origin. The source of the wave. Okay, where you start the disturbance, where you start the motion. Okay, so the source is located here, the origin. So origin, okay, is a beginning point, is a starting point. And then you look at the positions of every particle. Okay, the distance between origin and the particle, that one we call x. Okay, that one we call x. So make sure you know what is the difference between x and y. Okay, y is the distance from equilibrium position, or we say displacement. Most often we use displacement to describe y. Okay, we use displacement to describe y. So y is a vertical motion. Okay, vertical motion. This is y, and then x is a horizontal motion. All right. Okay, so always keep that in your mind. So this chapter, students, they often confuse. Okay, quite often students confuse between x and y. So make sure you know what is the difference between x and y. Okay, saya sentiasa tekankan apakah beza X dengan Y. Sebab apa? Sebab soalan sentiasa bagi maklumat untuk kedua-dua. So you yourself have to know which information belongs to X, which information belongs to Y. Okay. All right. So this equation, make sure you know because you will be asked to form equations in the exam. So the directions of the propagation, this one I also mentioned it just now. The things that you have to take note is the sign. Okay, you have a positive and also the negative sign. Okay, now this is where why we need to know what is the difference between X and Y, because you need to calculate two different velocity. So discuss particle vibrational velocity. Okay, you are looking at the velocity of one particles. Okay, this is a velocity for one particle. So what we do know about this particle is this particle is oscillating. It's oscillating up and down, and therefore it is actually a type of periodic motion. Aha. Okay, it is actually a type of periodic motion. So which means the way that we're going to use to solve it is actually very, very similar to the things that you learn in chapter 9. Okay, so velocity of the particles which oscillate about equilibrium position in simple harmonic motion. So we say it is a form of simple harmonic motion because it is a form of periodic motion, right? Periodic motion. So it keep moving back and forth around its equilibrium position, its original positions. Okay, therefore for the V, okay, it's equals to dy over dt. So in chapter 9, we use V is equals to dx over dt because x, we use it as a displacement of the oscillation. Just that in this chapter, we use a different symbol. We use y for displacement. Okay, so kamu jangan confuse ya. Chapter 9 kita guna x untuk mewakili displacement of oscillation. Chapter 10 kita guna y untuk mewakili displacement of oscillation. Dua chapter guna simbol berlainan. So by differentiating the displacements of the particles, V equals to dy over dt. Okay, so Vy equals to d over dt. Okay, so since y is equals to a sine omega t plus minus kx, this is the general equation just now. So we sub it into the equation. Now we differentiate a sine omega t plus minus x. So when it comes to this equation, because you want to differentiate with respect to time, okay, so the things that we are going to differentiate, okay, is the omega t, right? So if you differentiate it, what are you going to get? You're going to get v, okay, vy is actually equals to, okay, a omega sine omega t plus minus kx. Right? You differentiate omega t, you put it at the front. So Vy equals to a omega sine omega t plus kx. Wait, yeah, let me rewrite it. Oops. Okay, now actually it's correct already, yeah. I'm just going to rewrite it with a smaller pen, with a thinner pen, so that you can see clearly. So a omega sine omega t plus minus kx. Okay, so that is the equation for velocity, particles vibrational velocity. All right, what happens to just one particles? The velocity for just one particles at a particular moment, okay, at a given time. So in another equation, now this one is in terms of time because we differentiate it with respect to time. Okay, this one is in terms of time. What if we want to see what happens, okay, in terms of a distance? So actually there's another equation. Vy is equals to omega square root, okay, square root a square minus y square. All right, a square minus y square. So this is the second equation. So this is the equations that we say in terms of distance. All right, so the complete derivation, okay, is no longer in your syllabus, but for my tutorial, you can refer to the notes that I posted in our Google Classroom. Okay, I think my notes I did include a complete derivations there. Okay, saya ada masukkan derivations yang lengkap. So anda boleh rujuk sana nanti. Alright, but the first things that you have to know is that for a particle's displacement, a particle velocity, we use Vy equals to dy over dt. Okay, kita guna equations ini. Vy equals to dy over dt for particle vibrational velocity. So Vy in terms of time is Vy equals to a omega sine omega t plus minus kx based on the differentiations. And then in terms of distance, actually involve another set of derivation, right? So Vy is equals to omega square root a square minus y square. Okay, so derivation, I didn't put it in your notes. It's not, I didn't put it. Okay, they didn't include it in your notes. Okay, next. Okay, next we are going to look at what happens to wave propagation's velocity then. So just now we were talking about what happens to one particles. And another velocity in which we call wave velocity. Okay, so wave velocity, now we are looking at whole wave. Okay, whole wave. So what does it mean by whole wave? Oops. Okay, this is a whole wave. So this one, okay, we're going to look at what happens to this whole thing, all right, instead of just one particle. So just now we were looking at this yellow particle. Now we are going to look at the whole solid line. Okay, what happens to the solid line? So the wave velocity is the velocity at which the wave crest move forwards. Okay, so basically you just have to imagine the speed of the whole wave. Okay, the whole wave is moving. So figure shows the trough travel at a distance of a one wavelength in a time equals to one period. Okay, thus the wave velocity is equals to distance divided by times. So this whole wave, okay, from trough to trough, so this is 1 lambda, okay? So this 1 lambda, it takes time 1 period to travel from this blue color line, shift to the red color line. The whole wave is moving, okay? Not just one particle. The whole blue color wave, initially at times equals to 0. This is the position. This is located. This is the shape. And then after times t equals to a whole period, this whole blue color wave, they are being shifted to the new position to become this green color wave or on your red color wave. Okay, the red color wave. So this is the new position. Okay, this is the new position of the blue color wave after times t equals to period, time, capital letter T. Okay, so basically you take the blue color one, you put it here as a red color wave. Okay, kamu ambil dia, masukkan ke dalam red color punya wave. So initially, blue color wave located di sini. After times t equals to capital letter T, the whole wave move by that much. Okay, dia bergerak daripada blue color punya ke red color punya. So from here, we can calculate the speed, okay, which is equal to distance over time, which is your lambda over t. Okay, lambda over t. So if you expand the equation, okay, if you expand the equations, what are you going to get? You are going to get a general equation V is equals to F lambda, okay, because T is equals to 1 over F. So quite often we will use V equals to F lambda to calculate wave propagation velocity, right? So kamu kena tahu what is the difference between these two things. So V equals to F lambda, this is the equation for wave, not for particles. So don't get confused, okay? Don't get confused. So right now we have 3 V already. Kalau kamu tengok, kita sudah ada 3 jenis V. Okay, we have Vy equals to A omega sine omega t plus minus kx. And then we have a Vy equals to omega square root a square minus y square. And then we have V equals to F lambda. So you have to know when to use which one. So the first two belongs to particle. Okay, these are the informations that we use to calculate what happens in a particles. And V equals to F lambda, we use it for whole wave. Okay, whole wave. So you need to know what is the difference between these equations. Okay, exam, you will be given all this equation, but you need to know how to choose which to use. Okay, which to use in your questions. Okay, so boleh kan? So the last statement is very important, okay, because, okay, for a particle by vibrational velocity, you look at what happens to a particle. So the velocity of a particle, it varies with time, okay, and also it actually varies with the distance x. And then when it comes to wave velocity, it is constant. It doesn't change because you're looking at the whole motion. It depends on your frequency and also the wavelength. Frequency and the wavelength of a graph of a wave, it won't change throughout the motion. Assuming there's no energy loss, there's no external force acting on it. All right. So kena tahu beza, okay? So velocity of particle changes with time, varies with distance. Okay, changes with times or distance. Alright, dia bergantung pada dua benda. Whereas wave velocity is constant, okay, because the wave keep propagating at the same angular velocity. Okay, so this is the graph. You're going to sketch graph. Okay, I think I will stop right here, all right, because 10 minutes is not enough for me to explain the graph, okay, because I need to teach you how to sketch the graph and so on. So I will keep it for the next lesson because we need to learn how to shift graph some more. Okay, so I will keep it for next sections. What I want to do right now, okay, go to example 1. Okay, go to the example. So I will skip the table for now. Okay, I will come back to the table again in the next class, okay, in the following section. So now let's look at this example. The graph above show, okay, the displacement of a particles in a transverse progressive wave against a distance. So this is a y against a distance. So y against x graph, okay, at a particular instance. Write down the points where the speed of particles is 0. So where is the point when it is equals to 0? Oh yeah, this question is being very nice to use. It gives you the values already. So because, okay, now if you recall, now you're looking at particles, okay, you're looking at particles. So we know V is equals to dy over dt. And in mathematics, you already learned that the turning point is equals to 0, okay, when it comes to differentiations. So which means point P and point R, okay, is a point where the speed of particle is equal to 0, okay, not Q and S. Q and S just means, okay, Q, S, and T, it just means the displacement is equal to 0, okay, but not the speed. So speed is 0 at turning point, all right, speed, okay, speed is equals to 0 at turning point. Okay, because when the object reaches its highest position, it stops for a moment before it changes its direction. So the turning point is where the speed is equal to 0. So questions A, the answer is P and R. Okay, questions A, the answer is P and R. Questions B, write down the point where the accelerations of particle is maximum. So again, if you recall, okay, just now we were looking at a speed, which is V. Now we want to look at acceleration. So if you recall the things that we learned in chapter 9 in an oscillation, acceleration is maximum at turning point. So again, the answer is P and R. Okay, the answer is P and R. So acceleration is maximum at the turning point, right? So again, the answer is P and R. So P and R tadi. Okay, because it has the maximum changes. So you try to imagine the accelerations at the turning point and the accelerations at the velocity at the turning point and the velocity at the equilibrium position. The changes is the largest. Okay, it has the largest change, therefore the acceleration is maximum. Right? So pertukaran V yang paling banyak akan bagi kamu accelerations yang maximum. Because why? Because you calculate A by look at delta V, V final and V initial. So V initial happens at your equilibrium position. V final happens at your turning point. Okay, therefore at turning point, again, your acceleration is maximum. Write down the point where the velocity, of particle is opposite to each other. Okay, where the velocity of particle is opposite to each other. So point P and point R velocity is equal to 0. So what we are going to look at in question C, okay, for question C, the velocity of particle is a Q, S, and T. Okay, Q, S, and T. So we want to see which one they are opposite to each other. So let's look at point Q. Now, your particle start from 0, go through P, okay, go towards the directions of P, and then goes back to Q, which means at point Q, the particle is actually heading downwards. This is the direction of motion. Okay, the directions of vibrations. The directions of vibration. So it's actually going down. That's why you have the shape going towards R. Okay, at point P, the particle is now moving downwards. And then it keeps oscillating. And when it reaches point Q, this particle is actually oscillating up. Okay, the directions of oscillations, okay, of vibrations for particle at located at point S is going up. Okay, it's going up. And then it keeps moving. When it reaches point T, again, the particle is heading down. Okay, the particle is now oscillating downwards. Okay, vibrates to a negative Y direction. Okay, it vibrates to negative Y direction. So now we have Q, S, and T, and we also identify the directions of vibrations already. Where Q and T, now they are moving downwards, and point S is moving upwards. So the point where the velocity is opposite to each other is, okay, first pair, we have Q and S. This is number 1, okay, pair number 1. The second pair is S and T, okay, S and T. So S and T, they are also opposite to each other based on the diagrams given, okay. Q and S, satu pasangan, S and T, satu pasangan. Now, write down the point where the particles, they are in phase. So in phase means they are identical. They have same Y. They are moving towards same direction. Okay. So again, in phase means same directions. And then same displacement. Okay. Same displacement and same direction. We say they are in phase. So in this case, okay, in this case, we have Q and T. Okay, Q and T, they are located at same position, and according to the diagram, both of them, they are moving towards same direction. Okay, they are moving towards same direction. So they are in phase. Okay, they are in phase. So antiphase simply means same displacement but opposite direction. Okay, same displacement but opposite direction. Okay, now let's look at questions E. So state the amplitude and the wavelength of the wave. Okay, so amplitude and wavelength. So we have a Y against X graph. So amplitude means vertical component. So this is your amplitude. Okay, this is your amplitude. So amplitude is equals to 10 mm. Okay, A is equals to 10 mm. And then the other one is the wavelength. Wavelength, if you recall, okay, wavelength is equals to, okay, distance, okay, distance for one oscillation. Okay, distance from crest to crest or from trough to trough. So which means, okay, let's see, okay, let's say we start from origin. So origins, one complete oscillation is until 0.8. Okay, so from here to here, this is our 1 lambda. Okay, 1 lambda. So it is equals to 0.8. Okay, 0.8. So since the questions didn't give you the unit, okay, so we cannot write the unit. But F should be in terms of cm. Okay, F should be in terms of cm. This part is missing. So kamu sendiri tambah dalam soalan Anda. Okay, this part is missing from your books. So make a correction, okay? Add this into your book. Alright, tambah X and then bracket cm dalam buku Anda sebab dia tercicir masa cetak. So lambda is equal to 0.8 cm. Okay, lambda is equal to 0.8 cm. So done. Okay, so we're done with this example, and that marks the end for today's class. So in next lesson, I will teach you how to sketch wave. Okay, and then we're going to look at what happens in the superpositions of wave. And then we are going to go through a sound intensity as well, because that is just a very short subtopic. Okay, so in a following section, I will finish 10.2 and 10.3 with you. Okay, so maybe we'll take an additional hours to finish chapter 10, right? So that's all for today. You may leave the class now, right?
Thank you,
Thank you,
madam.
madam.
Thank you, madam.